We now have a traffic flow, but how do we ensure the information is correctly received and in the right order? This is the responsibility of the Transmission Control Protocol, TCP. In the next section of this training module, we will investigate the role of TCP. While IP is primarily designed to move information across a network, TCP is designed to allow for reliable, efficient communication between the application programs. TCP must be able to handle the possibility of lost datagrams, datagrams arriving in the wrong sequence, datagrams arriving unexpectedly after being delayed for long periods of time, and the delivery of duplicate datagrams. TCP is a transport layer component of the TCP IP protocol suite. It sits above IP in the protocol stack and provides reliable data delivery services. To put this into perspective, assuming you are writing one of the many thousands of networking applications that must exchange messages and data with other network computers, your program should be able to make a request of lower layer network protocols to have data delivered. At the same time, you should not need to write routines in your program that verify whether messages and data were received. This is the task that a reliable transport protocol such as TCP performs. TCP is a connection-oriented protocol. Before information can be exchanged between the sender and receiver, a virtual connection is established. TCP in turn uses IP to deliver information across a network. Interestingly, IP is a connectionless network protocol that does not guarantee reliable delivery. While IP provides efficient data delivery mechanisms, TCP makes up for the deficiencies by providing reliable services. TCP messages and data are encapsulated into IP datagrams, and IP delivers them across the network. During the development of the TCP IP protocol suite, it was argued that the connection-oriented features of TCP were unnecessary for some types of data transmissions, and that they created excess overhead and traffic. To overcome this issue, a connectionless User Datagram Protocol, or UDP, was created to provide an alternative application interface to IP. Both TCP and UDP use IP. While UDP resides in the transport layer, it does not have any of the reliability features of TCP. Perhaps the most important characteristic of TCP is that it sets up virtual end-to-end connections between two computers that need to exchange data. This connection extends across all the point-to-point connections that make up a typical router-connected network. This connection does not simply terminate at the network interface. It actually extends up into the application layer to a specific process running on the computer. Hence, TCP has to provide methods of identifying these specific endpoints. TCP connections are full duplex, two-way virtual channels that allow either end system to send data at any time. In this respect, a connection is really like having two separate transmit and receive channels. Buffers are used to hold incoming and outgoing data, so other activities are not held up by the communications process. The receiver can acknowledge receipt of IP datagrams to provide assurance of delivery to the sender. The acknowledge scheme is used in a number of ways, which will be discussed in detail on a future slide. Flow control provides a way for two systems to actively cooperate in the transmission of data to prevent overflows and lost datagrams caused by fast senders. This feature lets transmitting systems quickly adapt to the traffic loads on the network and/or the available buffers on the receiver. Sequencing is a technique for numbering datagrams so the receiver can put them back into the correct order and determine if datagrams are missing. A checksumming feature is used to ensure the integrity of packets. A TCP segment is the official name for what is often loosely referred to as a packet, where a packet is some package of information. A segment is the actual entity that TCP uses to exchange data with its peers. The segment is what gets encapsulated into an IP datagram and transmitted across the network. Segments typically have a 20-byte header and a variable length data field. The actual length of the TCP header is defined in the offset field contained in the header itself. The TCP header is in groups of 32 bits, Consequently, the offset is normally set to 5. The TCP header contains a number of important information fields. Keep in mind that either computer may send a segment that contains just header information and no data to provide the other computer with connection information. The source and destination fields contain the port number of the socket at the source and destination sides of the connection. These will be discussed in more detail on a future slide. The sequence number field contains information for the receiver, which is a sequence number that identifies the data segment and where it belongs in the stream of data that has already been sent. The receiver can use the sequence number to reorder segments that have arrived out of order. It can also indicate that a segment is missing. The acknowledgement number field is used by the receiver to indicate to the sender in a return message that it has received a previously sent segment. The number in the field is actually the sequence number for the next segment that the receiver expects. The sliding window field contains information about how much space is available in the receiver's buffers. The field is used by the receiver to inform the sender to slow down because the sender is sending faster than the receiver can process. Checksum provides an error-checking value to ensure the integrity of the segment. A number of bit codes serve as flags to indicate specific conditions, particularly during connection establishment and clearing. The user can add a pointer to indicate the location of urgent information within the data field, a number of special options, and user data. TCP achieves its reliability by sequencing each segment transmitted to allow the receiver to detect errored, missing, or out-of-sequence segments. This is done by including in each segment two fields: the sequence number, which contains the number of the first byte contained in the segment, and the acknowledgement number, which contains the number of the first byte in the segment that the receiver expects to process next. The receiver acknowledges correct receipt of segments by sending its own segments back to the sender with the ACK bit set to 1 and the acknowledgement sequence number set to the next byte it expects to receive. This means that one acknowledgement can act for several received segments. Note that an acknowledgement may be piggybacked on data being sent in the opposite direction. When TCP transmits a segment, it keeps a copy and starts a transmit timer. If the segment is not acknowledged by the time the timer runs out, then the segment is presumed to have been discarded due to error or lost and is retransmitted. If the receiver receives an out-of-sequence segment, it can either discard the segment and assume that it will be retransmitted, or store it until the missing segments have been received and then resequence the segments. When the receiver detects that a segment has been lost, or when a received segment has a bad checksum, it will request the retransmission of the segment by sending an ACK with the acknowledgement sequence number set to 1 more than the last correctly received byte. The sender will then retransmit the errored segment. Hence, TCP is able to overcome transmission errors in the lower layers of the end-to-end communication path. The way that TCP opens a connection is to use a three-way handshake. This ensures that each TCP host knows that the other is ready and which sequence number to expect in the first segment containing data. The first segment is from the initiator and contains the sequence number field set to an initial sequence number, ISN. The first data byte will actually be referenced using a number 1 more than this. The SYN bit is always set in this segment. The next segment, from the responder, acknowledges the receipt of the SYN segment by setting its acknowledgement number to 1 more than the received ISN and sends the sequence number equal to its own ISN. The SYN and ACK bits are always set in this segment. The third segment in the handshake, from the initiator, acknowledges the receipt of the responder's ISN by setting the acknowledgement number to 1 more than the received ISN. Again, the ACK bit is always set in this segment. The computers now have an open TCP connection between them. TCP closes a connection also using a three-way handshake in a very similar fashion to connection opening. Whenever either end of the connection, not always the initiator, has transmitted all of its data, then it may close the connection, meaning that it will not transmit any more data. This is known as the connection being half closed. This state still allows for the other end to send data and for the half-closed side to continue to acknowledge it. The procedure starts by either side issuing a segment with the FIN bit set. After this, one-way data transfer is allowed only. Once the other side has sent all its data and had it acknowledged, it will send a segment with both the ACK and FIN bits set. The closing response is a segment with the ACK bit set. Note that the sequence numbers show that a FIN bit, like a SYN bit, is actually counted as a data byte and increments the sequence number by 1. As already mentioned, TCP connections do not simply terminate at the network interface. They actually extend up into the application layer to a specific process running on the computer. TCP has to provide methods of identifying these specific endpoints. Each computer creates a socket, and the endpoints of the connection are attached to this socket. Each socket has an address called the port number. You can think of a socket as being like the telephones at either end of a phone call, and the port as being like a phone number. Port numbers use a 16-bit length. A process at a source computer must know the port number at which its target process resides, and so the IAB has published a list of port numbers for all commonly and sometimes uncommonly used processes. These well-known ports are in the range 0 to 255. For example, FTP uses port number 21, Telnet uses port number 23, Simple Mail Transfer, SNMP, uses port number 25. Port numbers can also be created as needed. If you write your own TCP IP application and service, you simply use a port number greater than 255 but less than 1024. In order to contact these ports, TCP sends the IP address and port number to be contacted, along with the data. The IP address is contained in the IP header, and the port number is contained in the TCP header. This combination of address and port number gives the process socket. The format for displaying this socket information is 131.120.33.5:21. For many processes, there will be multiple sessions open at any one time. Hence, the process socket must support a level of multiplexing. This is achieved by using the originating port number, which is dynamically allocated by the originating computer and must be greater than 1023 as a differentiation. We now have secure transmission between computers using TCP IP. But what applications will use it? In the final section of this training module, we will investigate the basic definitions of applications processes defined within the TCP IP protocol suite. The original Department of Defense definition of the TCP IP protocol suite defined these processes as providing a common communication language to successfully pass data between computer applications regardless of their operating system, manufacturer, method of formatting data, and speed and performance. There are dozens of TCP IP processes. We will take a look at the major ones covering network applications such as file-to-file transfer, email transmission, browsing the Internet, and managing networks. As already indicated, the TCP IP protocol suite, as originally defined by the US Department of Defense, contains more than just the two protocols. In addition to the Internet and host-to-host layers, it defines a layer called process applications. If we compare the DoD reference model with the OSI reference model, we can see that the process application layer corresponds with the top three layers in the OSI model. A whole lot of work gets done at this layer, and in it is found a vast array of protocols that combine to integrate the various activities and duties spanning the focus of the OSI session, presentation, and application layers. We'll be zooming in for a closer examination of the key protocols shortly. One of the original design goals of the Internet was to have applications that could run on different computer platforms and yet somehow communicate. The cavalry arrived in the form of the process application layer protocols, which address the ability of one application to communicate with another, regardless of the hardware platform, operating system, and other features of the two hosts. There are dozens of TCP IP processes, and anyone can write their own to carry out any particular function. A number of the most important processes covering file-to-file transfer, FTP, email, SNMP, web browsing, HTTP, and network component management, SNMP, will be investigated in detail in the following slides. The Telnet protocol is a very old and well-used protocol. The chameleon of protocols, Telnet's speciality is terminal emulation. It is designed for logging in to remote hosts and then acting like a local terminal. It is also used for logging into bridges and routers and other network devices for management purposes such as configuration. In both cases, Telnet enables a PC to act as if it is connected locally to the host or router and have access to all the features it would otherwise have. Telnet is provided with limited security features such as username and password protection. To enable emulation to work successfully, Telnet often requires extensive negotiations between the hosts so that the facilities offered by the server can be fully utilized at the client, and the client can mimic a server terminal successfully. Designed for client-server operation, X-Windows defines a protocol for writing client-server applications based on a graphical user interface. The idea was to allow a program, called a client, to run on one host and allow it to display on another host that was running a special program called a window server. This windowed terminal emulation offers the advantage of multiple sessions at the same time. Each session has its own window and menu options can be used to control the session as well as keystrokes. X-Windows offers a degree of user-friendly access to many different resources an organization may have in the network. Like the Microsoft MS-DOS operating system, Unix is non-graphical. Many Unix systems have been retrofitted by bolting on graphical user interfaces, GUI, based on the original X-Window protocols developed at MIT. The File Transfer Protocol, FTP, was written many years ago, specifically as part of the TCP IP suite. This is a grab-it-give-it protocol that affords us the luxury of transferring files. But FTP is not just a protocol, it's also a program. There are more than 50 commands defined for FTP, although most users only use a small subset of them. These commands allow FTP users to get and send files, change directories, rename files, list directories, and much more. To allow command flows, FTP uses two TCP connections, one for commands and one for data flows. With FTP, you don't have to care what operating system is on those remote hosts, because they all have TCP IP. This ability to transfer files to and from hosts running different operating systems is one of the best benefits of FTP. For example, suppose your local computer runs DOS with Microsoft Windows, and you need a file that's on a Unix system. No problem. Start up the FTP client application on your PC, connect to that Unix system, and get or send your file. FTP assumes that files are text-based and encoded in ASCII. When wishing to transfer other file types, such as Adobe's PDF, portable document format, or zipped files, FTP must be set to operate in the binary mode. This is obviously a powerful tool, and security must be provided. It is. Users must provide authentication at login with passwords and usernames placed there by system administrators. Limited access is also provided by using the anonymous username. With the advent of the World Wide Web, WWW, the direct use of FTP is depleting as the web interface hides the technicalities of FTP from the user. Remember, when your browser asks you if you want to save a file to the local disk, the transfer is still taking place using FTP. The Simple Mail Transfer Protocol, SMTP, is the protocol for Internet mail. It transfers email messages among computers. The message may go directly from the sender's computer to the recipient's, or the message may proceed through intermediary computers in a process known as store and forward. When we talk about services and applications in this section, remember that we are talking about TCP IP processes for the most part. You need to understand what is and what is not a TCP IP process. it may be different from what you think. Take email as an example. When you start a session to compose and send an email, the program you use to create the message is an application, but not a TCP IP process. Typically, these applications would be Lotus Notes or Microsoft Outlook. When you send the email message, the application hands it to a mail transfer agent, MTA. The MTA is the TCP IP process, and it uses the TCP IP protocol SNMP. The message moves from MTA to MTA until it gets to the addressee's computer. The addressee then uses their mail application to read the message. The communication between the mail application and the MTA does not have to be TCP IP, but the communication between MTAs does. The mail transfer agents run the message handling protocol called POP3, Post Office Protocol 3, or IMAP4, Internet Mail Access Protocol version 4. SNMP uses a basic request and response mechanism to transfer mail between POP3 or IMAP4 servers on the Internet. A few simple commands make this exchange possible. The commands are formed with ASCII text. The simple command structure makes it easy to build mail servers and clients for any platform. In 1988, the IAB realized that a problem existed due to the lack of multi-vendor network management from a single management station, and so they developed and published the Simple Network Management Protocol, SNMP. Just as doctors are better equipped to maintain the health of their patients when they have the patient's medical history in hand, network managers are at an advantage if they possess performance histories of the network in their care. SNMP is the protocol that provides for collection and manipulation of valuable network information. It gathers data by polling the devices on the network from a network management station, NMS, at fixed intervals, requiring them to disclose certain information. When all is well, SNMP receives something called a baseline, a report delimiting the operational traits of the healthy network. This handy protocol can also stand as a watchman over the network, quickly notifying managers of any sudden turn of events. These network watchmen are called agents, and when problems occur, agents send an alert called a trap to the management station. Management is achieved by all agents supporting a standard set of management information called the Management Information Base, MIB, which is accessible from the NMS by using a standard set of management commands defined by SNMP. Managers can choose an NMS independently of the vendors that supply the network devices. However, the MIB has been designed in such a way that vendors can add their own device-specific information to the standard MIB for access by their purpose-built NMS. Key enterprise network management systems that support SNMP are Hewlett-Packard's OpenView, IBM's NetView, Sun Microsystems' Sun Net Manager, and Cisco's CiscoWorks. NFS is a client-server distributed file service that provides transparent file sharing for network environments. NFS runs on a range of systems, from PCs to mainframes, in local or global environments. Multiple types of clients can access shared NFS file systems. DataQuest estimated that in 1997 there were over 12 million systems with NFS installed. NFS was originally written by a small team at Sun Microsystems in the 1980s, but was adopted by the IAB as RFCs in 1995. The object of NFS is to present files on remote hosts to users as if they were local. This means that files may be presented as if they are part of the local drives and directory systems. In fact, NFS works by utilizing various other separate protocols, namely the Remote Procedure Call, RPC, and External Data Representation, XDR. An important distinction between NFS and FTP is that NFS does not need to fully transfer a file to a client system. Instead, only the blocks of the file that the client needs are transferred across the network link, thus reducing network traffic. NFS uses UDP for data transport and therefore provides its own sequencing and reliability. In fact, NFS offers similar services to those of Novell NetWare and Microsoft NT, in that the network resources are presented to the user as if they are local. The user of the system often has no idea that the information they are working with actually resides on a network-based server. Unlike NT and NetWare, NFS is genuinely a networking operating system and does not dictate the operating system of the hosts, clients, or servers. Sun has now extended NFS to operate on the Internet with WebNFS. WebNFS basically makes information on NFS servers available to users of web browsers and Java applets over the Internet. The World Wide Web is built on top of the Internet and uses the TCP IP protocols to transport information between web clients and web servers. HyperText Transfer Protocol, HTTP, is the client-server protocol for the World Wide Web. It provides a way for a web browser to access a web server and request hypermedia documents created using hypertext markup language, HTML. HTML documents can contain hyperlinks to other places in the same document, to other documents at the same website, or documents at another website. HTTP is responsible for processing these links and providing a client-server communication protocol in general. HTTP is the command and control protocol that sets up communications between a client and a server and passes commands between the two systems. HTML is the document formatting language. The client makes a request to the web server, and the web server sends HTML information back to the client. The client's web browser properly formats and displays the HTML information from the server. The HTTP protocol can be secured using the SHTTP, Secure HTTP protocol, or some other protocol such as Secure Sockets layer. Encrypted information is transmitted on a secure channel to prevent eavesdropping. TCP IP is the most common networking protocol suite in use in data networks today. This dominance has been driven by the exponential growth in the business use of the Internet and enterprise-wide intranets. This trend is likely to continue, particularly with the adoption of IP as a possible protocol for the transmission of video and voice applications. The TCP IP protocol suite contains more than just the two basic protocols. It has additional protocols and applications to assist in building truly global and open systems. Protocols are provided to assist in address resolution, end-to-end routing, domain naming, and even computer application presentation. Using the TCP IP protocol suite, computers and workstations from any vendor can communicate on a company, national, or truly international basis. If the TCP IP protocol suite is at the heart of the Internet, then it is also at the heart of the future success of Nortel networks, who are committed to providing global data solutions to the enterprise and Internet service provider alike. To achieve this success, all customer-facing staff must have an understanding of the design, implementation, and applications of the TCP IP protocol suite. This training module has begun the process. Further information can be found on these CDs. Thank you for taking the Introduction to TCP IP training module. We hope that you now have understood some of the basic principles behind this critical data communications protocol suite. Thank you for your time.